Let's find a formula for the volume of a cone. But first, let's make sure you remember how to find the volume of a pyramid, like this pyramid over here. Its base is a square with side length 6, and its vertical height is 7. So what's the volume of this pyramid? If you're not sure, click down here to review. Nicely done. Next, let's look at a square pyramid and a cone together. As you can see, these two solids have the same vertical height, which we'll call h. And let's say their bases also have the same area, which we'll call A. Let's take a look at the different slices, also known as cross-sections, along the height for these two solids. How do the areas of the pyramid's cross-sections compare to the areas of the cone's cross-sections? Let's take a closer look at the two cross-sections halfway up the solids. Which of these cross-sections has a greater area? The one in the pyramid? The one in the cone? Or does it look like the two cross-sections have the same area? Exactly. These two cross-sections have the same area. Since they're both halfway up the solids, it turns out that they each have 1/4 the area of their solid's base. And not only do these slices have matching areas, everywhere along the height, these two solids have cross-sections with matching areas. So according to Cavalieri's principle, which of these solids has a greater volume? Is it the pyramid, the cone, or do they have equal volumes? And if you'd like to review Cavalieri's principle in 3 dimensions, click down here instead. Exactly right. These two solids have the same height, and everywhere along the height they have matching cross-sectional areas. So by Cavalieri's principle, they must have the same volume. So that means that the cone's volume, just like the pyramid's volume, is 1/3 times A, the area of its base, times its vertical height. And this is the formula for the volume of a cone. Just like a pyramid, it's 1/3 times the area of the base times the height. So take a look at this cone here. Its height is h, and its base is a circle with radius r. In terms of h and r, what's the volume of this cone? If you get stuck, click down here. Bingo! Just like a pyramid, the volume of a cone equals 1/3 times the area of the base times the height. And the base of a cone happens to be a circle, which you know has an area of pi r squared. So the volume of this cone equals 1/3 pi r squared times h. Let's try a sample problem with some numbers. Here's another cone whose radius is 2 and whose height is 3. What's the volume of this cone? Well done! So far we found that the volume of any cone or square pyramid equals 1/3 times the area of the base times the height. Let's take a quick look at a more exotic pyramid. This pyramid has a hexagonal base with an area of 9. And suppose the height of this pyramid is 5. If we really wanted to, we could use Cavalieri's principle again to compare the cross-sectional areas of this solid with a cone or a square pyramid. But instead of doing all that, why don't you make a clever guess? What's the volume of this right hexagonal pyramid? Very well done. The volume of any cone or pyramid is 1/3 times the area of the base times the height. Let's look at one last cone. Suppose its base has a radius of 5. So far, to find the volume of a cone, we've been using the vertical line that runs from the cone's tip, or apex, down to the base. And we've been calling the length of this line the height of the cone. But if you want to find the volume of a cone, it can be tough to measure its height, because it's a line that runs down the middle of the cone. It's usually easier to put a ruler on the side of the cone and measure the distance between the apex and a point on the circular base. This length is known as a cone's slant height. Let's say this cone has a slant height of 13. Now try finding the volume of this cone. This question is pretty tough, so if you get stuck, definitely click over here. Let's figure out a formula for the volume of a sphere in terms of its radius r. We'll be using Cavalieri's principle to find the volume of half of a sphere, also known as a hemisphere, and then we can double our answer at the end to find the volume of the complete sphere. But first, let's find the volumes of some other solids that involve circles. Here's a cone with the same radius r. And suppose the height of this cone is also r. What's the volume of this cone? If you're not sure, click down here to review. Exactly. The volume of a cone, just like the volume of a pyramid, is 1/3 times the area of the base times the vertical height, which is r for this cone. And the area of this cone's base is pi r squared. So the volume of this cone is 1/3 times pi r squared times r, or 1/3 pi r cubed. Great. Let's hold on to this fact over here. Next, let's look at a cylinder. Suppose this cylinder also has a radius of r, and its height is r as well. What's the volume of this cylinder? To review, click down here. Nicely done. Just like a prism, the volume of a cylinder is the area of its base times its vertical height, which is r for this cylinder. And once again, the area of the circular base is pi r squared. So the volume of this cylinder is pi r squared times r, or pi r cubed. Let's just hold on to this fact down here. So the volume of a cylinder with radius and height r is pi r cubed, and the volume of a cone with radius and height r is 1/3 pi r cubed. Next, let's flip the cone over and place it inside the cylinder. Now what's the volume of this region here that's inside the cylinder but outside the cone? You'll want to use these volumes of the cone and the cylinder to figure this out. Well done. Yes, the volume that's inside the cylinder but outside the cone is the volume of the cylinder, pi r cubed, minus the volume of the cone, 1/3 pi r cubed. Pi r cubed minus 1/3 pi r cubed leaves us with 2/3 pi r cubed. So this is the volume inside the cylinder but outside the cone. Let's hold on to this volume up here, and let's return to our hemisphere from the beginning. We'll be using Cavalieri's principle to find the volume of this hemisphere, and Cavalieri's principle looks at slices of solids. So here's a horizontal slice, or cross-section, of our hemisphere. What shape is this cross-section? In other words, what shape do you see if you slice a sphere? Right, this cross-section is a circle. Let's figure out what its radius is. We've been saying that the radius of our hemisphere is r, and let's suppose we've made this slice a distance x above the base of the hemisphere. So what's the radius of this circular slice? Well, this distance from the center of the sphere to the edge of this slice is also r, because r is the radius of the sphere. And notice that we have a right triangle here whose hypotenuse is r and one of whose legs is x. The other leg of this right triangle is the radius of our slice. So try using the Pythagorean Theorem to find an expression for this radius in terms of r and x. Very well done. The radius of our circular cross-section that's a height x above the base of the hemisphere is the square root of r squared minus x squared. Now, what's the area of this circular cross-section in terms of r and x? Precisely. The area of a circle is pi times its radius squared, and the radius of this circle is the square root of r squared minus x squared. And so the area of this circle is pi times the square root of r squared minus x squared squared. Squaring this expression cancels the square root. And let's also distribute the pi into the two terms inside the parentheses. And so this cross-sectional area, a height x above the base of the hemisphere, is pi r squared minus pi x squared. Let's hold on to this fact and take another look at our cone inside a cylinder, which had the same radius and height r. Cavalieri's principle is all about looking for matching cross-sectional areas, so let's look at the same cross-section in the cone and cylinder, a height x above the cylinder's base. Let's not worry about the cone just yet. Now in terms of r, what's the area of this circular cross-section of the cylinder? Right, the cross-section of the cylinder has an area of pi r squared. Now let's bring back the cone. Let's find the area of the circular cross-section that's inside the cone. Remember, just like in the hemisphere, we've been saying that this slice is a distance x above the base of the cylinder and the tip of the cone. And notice that the radius of the cone's circular cross-section has the same length x. So in terms of x, what's the area of the cone's circular cross-section? Nicely done. The cross-section of the cone, a height x above the base of the cylinder, has an area of pi x squared. Now we're almost there. Use these facts about the cylinder's cross-sectional area and the cone's cross-sectional area to find the area of this ring that's inside the cylinder but outside the cone. Bingo! The area of this ring is the area of this entire circle, which is the cylinder's cross-sectional area of pi r squared, minus the area of this smaller circle, which is the cone's cross-sectional area of pi x squared. And voila! You've just shown that at a height x above the bases of the hemisphere and the cylinder, the cross-sectional areas of this green slice and this dark blue slice are the same. They're both pi r squared minus pi x squared. And it turns out that the hemisphere and the region inside the cylinder but outside the cone have matching cross-sectional areas everywhere along their height. Let's see that one more time. The higher you go, the smaller this circle gets and the narrower this ring gets. Down here, the circle is larger and the ring is wider. Everywhere along the height, they really do have matching areas. So now it's time for the million-dollar question using Cavalieri's principle. As we've said, the hemisphere and the region inside the cylinder but outside the cone have the same height and matching cross-sectional areas everywhere along the height. So which has a greater volume? The hemisphere? The region inside the cylinder but outside the cone? Or do they have the same volume? And to review Cavalieri's principle instead, click over here. Yes, they have the same volume. Now remember, at the beginning of this lesson, you subtracted the volume of the cone from the volume of the cylinder to find that this region inside the cylinder but outside the cone has a volume of 2/3 pi r cubed. So, what's the volume of a hemisphere with radius r? Excellent! So a hemisphere with radius r also has a volume of 2/3 times pi r cubed. So this is the formula for the volume of half a sphere. And now, finally, what's the volume of the entire sphere with radius r? Brilliant! Yes, the entire sphere has twice the volume of the hemisphere, so we can multiply this formula by 2. Let's move the 2 into this expression by combining it with this 2 in the numerator to get 4. And so the volume of a sphere with radius r is 4/3 pi r cubed. Let's take this formula for a spin with one last numerical example. Here's a sphere with a radius of 3. What's its volume?